Hello and welcome everyone. I hope you're well. Welcome to the world's first webinar about recovered carbon black in plastic color concentrates. My name is Martin van Wolfersdorf and I will be your host and presenter today. So let's head over to PowerPoint and start the presentation. A little bit about me. I spent 14 years in the world of titanium dioxide white pigments, where I developed two of the high-performance masterbatch pigments for Huntsman. I then worked in the custom color masterbatch industry with Americam and served markets like turf and automotive interiors. And then I worked in carbon black with Cabot, where I was responsible for the sales of rubber blacks in Europe, Middle East, and Africa. Since 2014, I work as a global agency for strategy and marketing of chemicals, and I do business scouting, growth hacking, and you might know I'm specializing in recovered carbon black. These are some of my reference clients, but let's look at general tire recycling processes. Today we talk about recovered carbon black, so we're talking about the pyrolysis tire recycling process. There are other processes that also produce valuable materials, but today's webinar is about recovered carbon black in plastics. This is the agenda for today. I will first start to look at recovered carbon black, the state of technology and availability. Then we will look at plastic color concentrates and recovered carbon black in color concentrates as a third part. These are some of the participants today. I'm very happy to see that there is quite a few master batch companies, quite a few recovered carbon black producers, one carbon black producer, some machine producers, and also a couple of service companies and consultants. I would like to do a special welcome to François Terrat at Pro2Act, who is my mentor and who brought me to the topic of recovered carbon black. And also a special welcome to Jean-Paul Boissier, who has long time developed recovered carbon black within the ETRA Pyrolysis Forum. Welcome all. So let's talk about recovered carbon black and the state of technology. So how is recovered carbon black produced? It's produced by pyrolysis, which is a depolymerization at heat between 400 and 1000 degrees Celsius in an inert atmosphere. Many companies are using nitrogen, some companies are using steam. And we're producing about 10% of a hydrocarbon gas, which is used for the on-site energy creation. We get about 45% of a hydrocarbon oil, which can be sold as a combustible or even in the material valorization applications. And we get about 33% recovered carbon black. This is the profit center. And of course, this is the topic of this presentation. If you use whole tires, we also get 12% steel, which can be sold in the recycled steel markets. So what is recovered carbon black? It's important to know recovered carbon black is a composite of 4 material groups. Of course, we are recovering a mixture of the carbon blacks. There we have to see that tires consist of several carbon blacks. Each tire section, and tires are built up of between 10 and 14 sections. Each section contains its own carbon blacks and its own rubber polymers and additives. So we might recover 200 and 300 type of carbon blacks from the tread. We might recover 300 and 500 types of carbon blacks from the sidewall, 600 and other semi-reinforcing carbon blacks from the carcass. This is, of course, what we want to recover, and it's important to say feedstock control is very important to the quality of recovered carbon black. The 3 other groups we get, I call them a payload, because we get them because these materials are also in the tire or are produced by the process. The second group is the group of inorganics, also called ash. This could be amorphous silica from the fillers in the tread. In Europe, there is a lot of silica filler in the tread. It could also be crystalline silica. This is not so good. This could come from sand in the profile of the tire. So we have to clean the tires not to have the crystalline sand, because when we mill the recovered carbon black to below 10 micron, this will become respirable crystalline silica, which is considered a dangerous material. The same, we get zinc in the form of zinc sulfate. Zinc oxide is put in the rubber compound as a vulcanization activator. There should not be zinc oxide in the recovered carbon black because zinc oxide is a dangerous good with high ecotoxicity. And if we had zinc oxide in the recovered carbon black, we would have to declare this on the safety data sheet and with kind of ugly looking labels on the packaging. Zinc sulfide should be in the recovered carbon black, not zinc oxide. And we get of this, depending on the feedstock, whether we have car tires or truck tires, 15 to 20% ash content. 15% in the case of truck tires and 20 or even higher than 20% in the case of passenger car tires. And this is, as the composition of the carbon blacks, this is depending on the feedstock. Now we get two other groups of materials, and these come from the depolymerized rubber polymer. There could be volatiles, organic volatiles on the recovered carbon black. This is also not good because it doesn't pick up the chance, the opportunity of value creation of having a low PAH content. PAH are the polycyclic aromatic hydrocarbons, and you might know that first of all, the industry demands a very low content of PAH, but also the type of virgin carbon blacks that have low PAH content are much more expensive than the normal carbon blacks. So here we can create value with a very low PAH content. For that, we need a low total content of volatile hydrocarbons. So I'm saying 0 to 3%. 3% is the maximum we can bear, bearing in mind that we might have 1%, 1.5% of moisture. The rest, if it is aliphatic hydrocarbons, this is good, but they shouldn't be aromatic, and we need to analyze that. The fourth component is also process depending. And the fourth component is if we have volatile hydrocarbons and the residence time of the process, for example, in a batch process is very long, these can actually solidify. And now in coloring applications, this could be a nice benefit because we'll see a little bit later on the carbon content of the recovered carbon black is very important for delivering the black color. In the rubber, this chow of carbonaceous residues of fresh carbon is not so good. So generally, I would say if we can reduce the amount of fresh carbon, we should. Now let's look at how different carbon blacks and recovered carbon blacks look like. The important information about carbon black is there's microparticles in the size between 20 microns and about 100 microns. 20 microns in the case of N100 grade carbon black and 100 micron in the case of 700 range ASTM carbon blacks. Now, you see the microparticles. These microparticles, nano-sized microparticles, are never alone. They are clustered into aggregates, and these aggregates are fused together at about 1700 degrees. This is the smallest version of the carbon black we can have in any kind of system. The size is 0.05 micron to 0.5 micron. So very small, and the aggregate size distribution is very important for the performance in tinting and coloring. Now there's agglomerates. They could be several aggregates clustering together with van der Waals forces. They could have any size between 1 micron and 100 micron. And in some applications like rubber extrusion, the grit is very important. Grit can come from oversized particles coming from the quenching water or the pelletizing water. And this typically has the size of 125 micron. So there is a special rubber extrusion carbon black grades that are using demineralized water for quenching and pelletizing to avoid these salts. Also, typically carbon blacks are unmilled or they're coarsely hammer milled. Now let's look at a recovered carbon black. Recovered carbon black contains carbon blacks which are recovered, so it can be a cuneiform grade-like. It can have the structure similar as carbon black. The microparticles are quite different though, because here we have a heterogeneous material. It's not only carbon black. We have the ash content, we have carbonaceous residues, we might have some volatiles. And the microparticles are anything between 20 nanometers, which is the smallest size of the carbon black, and 500 nanometers, which could be bigger particles of the ash content. We also have aggregates. However, here in the pyrolysis, we don't have the high temperatures of the carbon black manufacturing reactor. We have temperatures maybe between 350 and on the upper side at 700 degrees Celsius. Now we have a very large aggregate size between about 1 micron and 1 millimeter, or even several millimeters. So there is a need of milling for recovered carbon black. And the milling should in any case be below 100 micron. It's very difficult to have any performance in rubbers and plastics for recovered carbon black that is unmilled and might be much bigger than 100 micron. A really good or standard quality recovered carbon black might be below 45 micron. For plastics and coloring, I really recommend finer milling, which could be 20 micron. We will get to the specification for coloring recovered carbon black in a moment. In some cases, actually, producers of recovered carbon black are milling to below 2 micron. This is the case for very low viscosity systems. For example, if you want to use recovered carbon black as color in paints or inks. So let's look at a specification for coloring applications. At first, it is important to know, and this also comes on the safety data sheets, the model mixture of recovered carbon black is carbon black, silica, and zinc sulfate. So in the carbon black can be anything between 80 and 90%. This is feedstock depending, as we discussed before. It can be 3 to 10% silica, or even slightly higher than 10% if we have very high content, silica content feedstock. Zinc sulfate could be 6 to 10%, for example. Now, the most important property is the consistency. At the moment, at this time, there is no confirmed testing method from ASTM. You might know ASTM has a workgroup D36 that is working on norms and specifications for recovered carbon black. So at the moment, the exact specification of the consistency is pending. However, in my opinion, consistency should start with a consistent TGA result. TGA is a thermogravimetric analysis, and it analyzes how much volatiles you have, how much carbon and how much ash in the feedstock. In the recovered carbon black. We can adapt the method ISO 9924 Part 2 for the TGA, measuring the consistency. If we don't have a consistent TGA result, it's very difficult to have consistent application results. Now, the carbon comes from the TGA, the ash comes from the TGA. I would recommend having more than 82% carbon for a coloring recovered carbon black, which means the ash content should be less than 15%. Of course, if you can have a recovered carbon black that has no ash content, that would be even better. Carbon char might be between 3 and 22%. We'll get back to the carbon char in one of the next slides. This is depending on the feedstock, on the process type, but also on the process conditions. The total volatiles should be 1 to 1.5%, meaning this should be moisture only, not organic volatiles. In turn, the PAH content as measured by the toluene transmittance ASTM D1618 should be between 80 and 98% transmission. This is depending on the process type, but also on the process conditions. If we have a result like that in the toluene transmittance, we can chemically test for benzoapyrene, which is the most nasty compound of PAH. And we can test by gas chromatography and mass spectroscopy, for example, with an ISO 18287. What we want is less than 1 ppm benzoapyrene. Also, the group of the most 8 common PAH compounds with the same method should be below 8 ppm. We should have no contaminations like metal. We should have no textile contamination, no crystalline silica, and no zinc oxide. And as mentioned before, we should be milling to D99 of 20 microns. And D99 means that 90% of the particles, 99% of the particles are smaller than 20 micron. How do we measure this? There's an ISO test for it, 13320. This is measured by laser diffraction with a CLAS or Malvern Mastersizer system. We have to bear in mind that these particle analysis thinks that the particles are spheric particles, but as we have seen with the normal carbon black, also the shape of the recovered carbon black probably is not spherical. So this measurement is an approximate measurement. Now also we need to pelletize the recovered carbon black. The pelletizing is for convenience of handling, low dust handling, also for better conveying in pneumatic systems. And here it is important to have a pellet hardness, which is not too soft, because then the pellet will break up in transport and the customer will just receive some powder. It shouldn't be too hard either, because then it cannot be broken up in the dispersion processes in polymers. In our case, we'll get to that. That might be either an internal mixer, or that might be a twin screw extruder. And if we don't disperse the recovered carbon black, we cannot get any color performance. That counts for plastics as well for rubber processes. So let's look at the process choices. Very often I'm asked the question, is a batch process better or continuous process? So let's look at both processes. Before, let's look at the little chart at the top right corner, where I indicate the CAPEX and the OPEX costs of typical processes. It's very small, but you can see the blue dots are European technologies. There's two red dots, which are Chinese technologies. There's the American flag for the American technologies, one British technology, and there is one Swiss technology. And what I can say is, for the CAPEX, I see the reasonable CAPEX for Western technology is about 500 euros per ton of tire capacity. And a reasonable operating cost is below 200 euros per ton of tire capacity. So it's very difficult if the capex is much more expensive than the norm. Then you have a need for very high quality recovered carbon black and other products to have a good business case. However, I frequently recommend investors to increase the capex if you can reduce the opex. So a combination of a high capex and a low opex is a good strategy. Let's look at batch pyrolysis. So batch kilns are very simple kilns, and it can be very tight, airtight, which is one of the problems of continuous kilns. They also can take whole tire feed. So that is working on reducing the operational cost, because we don't have to granulate the feed, the tire feedstock, so that it can be conveyed in the continuous systems. They're kind of difficult to scale up. One example is Pyrolyx, and for the capacity of 36,000 tons of tire feedstock, they required 20 kilns. Now they have an automatic feeding system, but these are considerations for large scale. Probably a continuous system is easier to set up and to scale up. Typically, the batch kiln has poor thermal efficiency, because to unload the batch kiln, we need to cool down to open the kiln and get out the metal and raw recovered carbon black. Typically also, we talked about the char. Typically, the batch kiln is producing higher char or carbonaceous residue on the raw recovered carbon black. Now, in our case, for the coloring application, that could be a good thing. That could be a bonus. But it is different in continuous kilns. Continuous pyrolysis kilns could be rotary kilns. On the simple side, could be auger kilns. Very often there's multiple auger steps in the reactor. It could be a dripping bed reactor. There's one company which is Pyrum that has a dripping bed reactor with no moving parts. So there we can have a continuous system which is really airtight, which is a good advantage. Continuous pyrolysis kilns are easy to scale up. They have a good energy efficiency. However, as I said, typically they require a very small granulate feed. And typically there's tightness issues. You might have heard of the fire at Black Bear Carbon. That was hydrocarbon gas getting out and meeting hot surfaces and then causing the fire. And this is not the only technology and the only company that had this challenge. Typically also because in the continuous kiln we have a set temperature and we have a limited residence time until the raw recovered carbon black leaves the reactor. Typically continuous pyrolysis tends to have high volatiles on the raw recovered carbon black. That could be, for example, 3%. Now let's look at some examples. In the batch kiln, we have, for example, New Energy in Hungary. We have Scandinavian Envirotech in Sweden. We have Pyrolix in Germany and the US. And we have Tirebirth in Italy. Tirebirth is a microwave system. You might know that I quite like microwave systems for the very efficient heat transfer and the very short reaction time. On the continuous side, we have Clean Industry with a plant in Poland. We have Boulder Industries with a plant in the US. Aquafuels, again, a plant in Poland. Contact, also Poland. Pyrum, we mentioned before. Alpha Carbon, plant in France. And we'll hear from Alpha Carbon in a moment. Rotawave is a semi-microwave process with a continuous rotary kiln technology in the UK, and Delta Energy, also rotary kiln technology in the US. What is the recovered carbon black availability? Everybody is interested in recovered carbon black, but how do the supplies look? And actually, the supplies look not as high as the potential demand. I reckon in Europe, as of 2020, pre-COVID scenario, there could have been about 180,000 tons demand for recovered carbon black. However, there is only 28,000 tons supply in Europe. And this supply I split into three quality categories. RCB1, which is the top quality, which is the type of quality of the specification I mentioned a moment ago. There's only 10,000 tons available, and this is the wider Europe, including countries like Ukraine, Russia, Belarus, Turkey. There is about 4 kilotons of an intermediate quality, maybe where the volatile specification is not met or several criteria are not met of the specification mentioned. And there's a big part, more than half of it, of 14 kilotons, which are raw. Is raw quality, so it's unrefined. Probably the feedstock is not controlled. Probably there's high volatiles. So this quality, 14,000 tons, is not usable for plastic applications. In China and India, we have higher availability. I reckon in India there's maybe 30,000 tons. In China, 50,000 tons. But then we would have to look at which quality category those might fall in. In Middle East, Africa, I reckon we have less than 5,000 tons availability. In the US, maybe about 10,000 tons, similar to Europe. Now let's look at plastic color concentrates. You might have heard not about plastic color concentrates, but about compounds. So what is a compound? In the US, it's also called a pre-color. So it's a ready-made mixture which the converter can put, for example, into injection molding for producing a nice plastic automotive mid-console as pictured in this slide. The compounder needs to mix the resin or several resins. Very often there's up to 5-6 resins in one compound. For the black, he would mix carbon black, of course. There also is white pigment in there, for example, for the UV reflectance. There might be other pigments to correct for the color, red and blue pigments. There might be antioxidants, there might be plasticizers, surfactants, UV stabilizers, anti-scratch agents, and the list continues. So this is quite complex, and it's a little bit like a cook in the kitchen that is doing the recipe so that the meal is perfect. Here we want specific performance in automotive. We want the plastic to be scratch resistant, UV resistant. The color needs to look nice, and it needs to be glossy and everything. When is the compound route used? So this is used for large volume demands. Typically in the European automotive plastics, ready-made compounds are used. Also the quality consistency, because once you have the quality stable, you can produce a large volume of the compound. However, once produced, you cannot correct the compound. And also, you cannot really adjust to small volumes. This is for the big volumes like used in the automotive industry. And one negative aspect is that you need a large storage for all these different compounds. The second route to color is with concentrates. In Europe, this is called masterbatch. In the US, it's called concentrates, or it's called color at press because the color is only added at the injection press, or it's also called natural plus. Here we have the masterbatcher or color concentrate maker making a concentrate, and then the converter is diluting that concentrate to the relevant concentration he needs with clear virgin polymer. And this is much more flexible a system. It could be used for medium volume demand or even for small volume demand. It's used in the packaging industry. Now the automotive plastics in the US is mainly going the master batch route. And even if the master batch has some quality issues, we can correct at the press by mixing another master batch and by correcting the dosing rate. Also, we can optimize the storage because we can store several master batches which don't take high volume, and then we store the clear polymer that can be used for any kind of color for diluting to the relevant composition. What kind of master batches are there? So there are single pigment dispersions, there's additive master batch, for example, and combi master batches. Keep in mind that master batch is not so much a product, it's much more a dispersion service, because all these ingredients for plastics can only work if they are very well dispersed. And that is what the master batch company is delivering. In the single pigment dispersions, SPDs, there is, of course, a specialist for black, white, and color. In the black single pigment dispersions industry, we have Cabot, we have Hubron, also present in the webinar. We have modern dispersions present in the webinar. Citra, Premix, Compuestos, Kimpas, colloids also present in the webinar. Cezanne, Chromex, and we have megastars like Schulman, Ampersand, Poly1, Clariant. We will hear about some of those a bit later on. In the white area, which is a titanium dioxide concentrate, we mainly have the megastars, the big master batch companies like Ampersand, Schulman, Poly1, Clariant. And then, of course, there's the very fractioned market of color single pigment dispersions. We can have additive master batches, and the most common filler is calcium carbonate. There's a concentration of these companies in Spain that do calcium carbonate concentrates, which are Granic, Compuestos, and Plasper. And then, of course, we have additive master batches of anti-slip, anti-block, anti-UV, and all the additives. The most complex master batch is a combi master batch. That is what I showed you for the automotive compound. There is thousands of small color houses everywhere in the world, very specialized to the local market. And the combi master batch can include, as I showed, several pigments, several additives, or a combination of both several pigments and additives. And it could be, for example, the Coca-Cola red in polypropylene for crates. Let's look at Resins, because also it's important to understand what kind of plastic resin is important for the master batch. The most popular plastic resin is polyethylene, and this is on the back of packaging films, shopping bags, garbage bags, and for low density polyethylene, high density could be bottles or toys. All these resins have different melting points, and they have a different melt viscosity or melt flow index. The second most popular is polypropylene, followed by polystyrene. Polypropylene could be furniture, car interiors, consumer carpet. Polystyrene could be vending cups or disposable cutlery. The kind of cutlery people don't want to use anymore, which probably is good. Polyester, engineering plastic could be soft drink and mineral water bottles, synthetic fibers for sports gear, for example. Polyamide, also engineering plastic polymer, is used as a metal replacement, furniture, automotive under the hood, and office carpet. ABS could be on your car bumper, any exterior automotive trim, casings for electronic devices like your computer, for example, Lego bricks. And then there is something called universal carrier. This is like a wax carrier, and normally master batches make the color concentrate for the resin of the relevant end-use application. So if the end-use application is, for example, a low-density polyethylene, you need a master batch with that resin. However, you can use universal carrier waxes. They can be used in several end-use resins. So that is more flexible in the master batch market. Let's look at how master batches are produced. I mentioned internal mixers, but by far the twin screw extruder is the most common master batch production technology. So you have the extruder, which is depicted here. Here I'm showing picture from Leistritz. You might have a feeder system. Now this is a small extruder, but in the large extruder you might have pneumatic conveying of the premix, or you might have several multiple feeds. The screw, as you can see in the middle of the slide, has different sections. The first section is for melting the polymer. Then for dispersing the polymer with all the ingredients, there might be vents, there might be open vents. At the end of the extrusion, there might be a vacuum vent to take out the volatiles. So after the dispersion units, there could be distribution screw elements. And at the end of the screw, we need to build up the pressure for the extrusion. Then we might have a screen pack, which is like a sieve pack, which is straining for oversized particles. And the oversized particle, they could be really varying depending on the pigment. Generally, for standard plastics, we might use a 45 micron screen, which is screening everything above 45 micron. For high performance plastics, we might use 25 micron. This is already getting into the application of polypropylene fibers, for example. And this is the size of a white blood cell, so very, very small. Synthetic fibers might even require 10 micron screening, which is the size of a red blood cell, very, very small. After the screen pack, we might go into a water bath strand cooling, and then the plastic is cooled and solidified, but we need to dry the water off. We might have an air blade dryer, and then we need to cut the strand into little pellets, cylinder-shaped pellets, or if you have a water bath cutter, also underwater cutter, we have more pellets that are more shaped like lentils. Now, for master batch, what we are looking for is color. So in our case, for recovered carbon black in master batches, we are looking for black color. It's important to know how to measure color. And there is many color systems. Color is a very complex topic, but by far the most popular system is the CLAP system. And I have to say color and beauty is in the eye of the beholder. So color might depend on the eye, might depend on the machine. It depends certainly on the light source as well. You might have bought any trouser or shirt, and in the artificial light of the shop, it had a completely different color than in the natural light on the street. So typically in the color measurement for masterbatch, people use generalized, standardized colors. And that could be the CD64, which is a mid-daylight artificial color source, very defined. Now, the CLAB system has three properties. The L is the lightness, and it goes from 100%, which is white, to 0%, which is black. We'll look at the black side, the dark side of the world, and the next slide. But let me explain first. The B-axis is between the blue and the yellow, and the A-axis is between the green and the red. And if A or B are close to 0, we're close to the L-axis. And the visibility threshold for the delta B, so the difference between two B star measurements, are 0.3. And then looking at the masterbatch, we have several mechanisms the light can engage with our pigments. That could be reflection, which is the case of titanium dioxide, with the highest refractive index of all materials. This is the reason titanium dioxide is used as a white pigment, because all the light is reflected. It could be absorption, which is the case of carbon black. So we expect from carbon black, and then also from recovered carbon black, to absorb all the light and to appear black, because black is the absence of any light. And then we might have scattering effects when the light comes on the particle and is scattered from that particle. One thing about coloring differences, this is measured with a delta E, and you see the formula on the right-hand side of the slide. A color difference of delta E equal to 1 is barely perceptible if the two colors don't touch. So if you have one color next to the other, we can compare those colors more easily than if we look first at one color and then at another color. We'll test that in a moment. Then another thing which is very important is the metaimmersion. And this is the color difference under different light sources. Like I mentioned, natural light and the artificial light in the shop. The color consistency is very important for companies, for example, in automotive plastics, that the car color or interior color looks the same under artificial light as in the sunlight outside the garage. Now let's look at the black side, the dark side of life. Here we have the lower bottom of the color system. You can see the L-axis in the middle. You can see the A-axis and the B-axis. And I marked one point, which is a RAL color. You might know the RAL swatches. This is jet black, and jet black typically is regarded as the blackest black. And you can actually see, if your monitor is good, the black box on the right-hand side, that is jet black color. A little hint, if you want to simulate colors on PowerPoint, knowing that probably the representation of that color on the screen might not be 100% because your monitor is not calibrated. But if you want to get any color into PowerPoint or Excel or Word, convert the LIB coordinates to hex color, because you can input the hex color in PowerPoint, Excel, and Word. There's also the red, green, and blue system, but we're not using that at the moment. So you can see the L color of jet black RAL 9005 is pretty low. It's 4, and B is really small, close to the axis, and A is also close to the axis. B is slightly negative, so we have some aspect of blueness. Generally, if we have an L star of smaller than 5, we can say this is a black color. Everything above 5 is more a dark gray color. We'll have a look at that in a moment. And if we say L is smaller than 5, we can say we have less than 1% light reflection. Now, if the L star is lower than 1, we can say we have a deep black. We can have lower than 0.1% light reflection. This is the case for automotive top coat applications, and generally this deep black cannot be accomplished anymore by the standard furnace carbon black process, which makes all the rubber blacks and normal carbon blacks for plastic applications. But this is the gas black process, which produces very, very small particle sizes. We'll see later on in the presentation why this particle size is so important. Now let's look at the RAL number 9005 jet black. This is a true, or should be a true representation of jet black. We've discussed the LAB values already. Now, if you compare with signal black, I go back and forth. You can see signal black is much more gray, much lighter. As you can see, I highlighted the L star value of 17. It's much higher in the L axis. Now we go down and we look at shades. The shade is the redness or the greenness, blueness or yellowness of the black. And here we can say this is a black brown because the A is close to 2. L is 8, so it's pretty dark, not really super dark, but this is the black brown RAL 8022. Now, very often in coloring applications, we don't really want the brown shade or the yellowish shade, which is linked to some dirty aspects of the color. We want a clear and crispy blue. So the RAL 5004 is the black blue. You can see the L is 11. So it's, let's say, a dark gray. It's not a true black. The A is pretty neutral, close to 0. But the B is negative, which means blue. It's negative by -7, almost 7.5. Now we got some sort of grays, which is the traffic black 9017. Also, it's a gray because the L is 16. A and B are pretty neutral. And we have the graphite black. The graphite is a gray, right? It's not a black. L is 16. The B is a bit more in the blue area, which is -1.7. And these are all the colors together. And as I said, all the colors, if they're next to each other, we can make out the differences much easier. And when you look at the black blue, you can really see the blue tonality. Black brown is not looking very brownish, but if you compare it to black blue, you can see the difference. Signal black, quite light gray, and jet black is the only one of these colors that is looking really, really black. Now, this is all accomplished, of course, with carbon blacks. I'm showing you this chart. It's a very busy chart. Probably I could have taken out some information, but this is the carbon black spectrum with some applications in plastics. And there's 2 or 3 key messages I want to convey to you with that slide. On the y-axis, we have the structure, which is measured with the oil adsorption of the carbon black. So the higher, the more structured is the carbon black. And on the x-axis, we have the standard thickness surface area, which is the Brunner-Emmert-Teller nitrogen adsorption in a monolayer, just showing the external surface, not including the internal surface of the micropores, mesopores. Now, what you can see is different ASTM carbon blacks that are the N numbers and the gray dots. And we have the semi-reinforcing, also called low color, on the left-hand bottom. In the middle of the chart, we have medium color. This is the rubber black N330, for example, which is also called high abrasion furnace HUF carbon black. Then we have higher surface, providing higher color. And the higher surface is a smaller particle. So here already we can say smaller particle has a higher color. We have the 200 range of rubber blacks, which are on the plastics side of the world, are called ISAF, intermediate super abrasion furnace. Or we can have the N100 type of rubber blacks, which are called super abrasion furnace. And you can see at the edges of this chart the effect of going higher structure, bigger particle or smaller particle. And one of the problems is if you go high color and we have a high structure, we get high viscosity and we're limited in the loading. And then there is a couple of specialty blacks that have the high surface for the high color, but they have a low structure, which you can see at the bottom right corner. This could be, for example, Birla Raven 2000, which is used in automotive interiors or in PET polyester bottle preforms. One interesting fact also is we looked at the tonality on the screen of the different blacks and grays. There is also the undertone. Now, the undertone is the tonality when you mix the black pigment with the white pigment, and then you get a certain shade. But it's totally different. And while in the mass tone or in the master batch, we have a blue tonality if we have smaller particles and high surface. In the undertone, if we mix, for example, a black and a white, the bigger the carbon black particles are, the more blue the mixture of the color will look like. So let's look at types of black master batches. We talked about the polymers, and we have a combination here of all the polymers and the different carbon blacks. So we talked about polyethylene, polypropylene, polystyrene, which are polyolefin resins, for example, polyester, polyamide, or universal carrier wax. And on the carbon black side, we have low color, medium color, high color. We have a specific high jet black carbon black. And then we can go back a little bit. On the right-hand side of the high color would be a P-type, but the P-type is also pure. So it has a low PAH. It's fit for food contact. We'll get to that in a moment as well. So this is summarizing all the different combinations. We can see the tonality, and as mentioned, bigger particles, so semi-reinforcing or low color carbon blacks have a brown tonality, but in the tint they get a bluish undertone. And we have varying concentrations. That depends on the resin, but that depends also on the carbon black. Now, we have talked about recovered carbon black and we've talked about master batch. Let's talk about recovered carbon black in master batch. And I want to give you a couple of showcases of companies that already have developed recovered carbon black master batches. I think the first company to have recovered carbon black in master batches was Modern Dispersions in the US. They introduced on the Plastics Fair K 2016 in Düsseldorf. They are 40% recovered carbon black master batch. It's also combined with recycled carrier resin, so it's 100% recycled product. I think that's very good to have 100% recycled product. The letdown ratio is 2 to 5%. Applications, all applications including automotive and office furniture. Eco impact, so it saves oil and it saves also, it lowers the carbon burden. Now all this info is from Modern Dispersions, including the picture. Now we look at the Reco Black 216 by Ampersand. Ampersand have a site in Terre Haute, and you might know that the pyrolysis company Pyrolix has a site in Terre Haute as well. So this is a collaboration between Ampersand and Pyrolix. It's a 40% recovered carbon black master batch. This time we have 95% recycled content. There might be some additives or it might be some virgin polymer added to the mix. Applications are stated general purpose industrial and consumer goods, packaging and flexible infrastructure applications. Eco impact, oil saving, of course, and carbon burden saving. Interestingly, Ampersand mentioned the combined use of odor scavenger. Typically, if a master batch contains post-consumer recycled carrier resin, it might have some odor, because there might have been some food packaging, and if we separate the food packaging from the rubbish, there is still food in there. Typically, consumer recycled resins have some odor. Industrial recycled resins might not have an odor that is coming, for example, from shrink wrap film. Those tend to be cleaner typically. So it's a smart idea to use an odor scavengers to capture the odors, to mask the odors from the recycled polyethylene. Again, all info and the image from Ampersand. Now, PolyOne also has a collaboration with Boulder Industries, and the OnColor RC Environmental Black by PolyOne contains Boulder Black. Boulder Black, as far as I know, is the only brand for recovered carbon black. I think this is very good to bring the recovered carbon black product in the market and to position it at a very high value. It's a range of carrier polymers. This is very good because it gives flexibility and the applications. Applications quoted are automotive, appliances, electronics, and office furniture. The eco impact, the RCB uses 90% less water and 61% less electric power and emits 90% less carbon dioxide. Regulatory aspects we will cover actually in the last slide of the presentation, but I think it's good that PolyOne mentioned REACH compliance and RoHS compliance. Again, all info is from PolyOne and the image. Cabot also has a recovered carbon black master batch, the Tech Black 85. This is interesting because it contains reclaimed carbons. I would say these are recovered carbon blacks. It also contains post-industrial carbon black. So this is out of specification carbon black, which cannot be sold, and which normally is being bled into normal carbon black at a very low rate of 1%. But if this can be used for a plastic master batch, that's also a good application. And it contains recycled polymers. Cabot make no statement of whether it's post-consumer or post-industrial. And there's a range of carrier polymers. Applications are quoted as compounding, injection molding, and non-critical film applications in industrial packaging and consumer markets. Again, all info is, and the image is from Cabot. Then we get the RC Black range by Chromex, and I really like this because it's the full range of resins. It is between 20 and 50% concentration of the carbon black part in the recovered carbon black. This is quite smart because keep in mind that in the recovered carbon black we have an ash content, and only the carbon black is a coloring component in the recovered carbon black. So Chromex specify not the total RCB content, but specify the carbon black part in the master batch. So the total recovered carbon black content is way above 20 to 50%. What I like also is it's almost a complete range in terms of the resins. It's polyethylene, polypropylene, styrene, polyamide, ABS, EVA, and PET, also called polyester. These carrier resins are not recycled, but on demand, I think Chromex would also make a 100% recycled master batch of recycled carbon black in recycled polymer. Applications, a long list by resins, typical applications for this kind of resins. And again, all info and the image is from Chromex. Now let's go to testing recovered carbon black master batch dispersion. And here I'm thankful for the data from Alpha Carbon and the fact that they allowed me to show this data. We said that the color performance is very depending on the dispersion. And how do we test dispersion? There is an international standard for the filter pressure value. Here we are extruding with a screen pack, and we're measuring not the particles that are on the screen pack in ppm, but we're measuring the counter pressure, which increases, as you can see on the right-hand chart, which increases with the amount of extruded master batch. This norm is the DIN EN ISO 23900 from last year, 2019. It formerly was the EN 13900 from 2005. What is very important, because actually on the chart here you can see this is a failed screen pack test. But the interesting information is Here we have two carbon blacks, a Huff type N330 type of carbon black and a recovered carbon black. And both failed. And both failed. Why? Because the screen pack was very, very small. Actually, in that filter test, the broadest, the biggest kind of sieve opening is 25 micron, which you can recall from early on is already used for high performance plastics. And then the screen pack 2 is even worse. It's less than that. It's 14 micron. And the screen pack 3 is 10 micron, which is used for synthetic fibers. So perhaps the recommendation here is a 45 micron screen pack is best for the recovered carbon black master batches. Interestingly, if the filter pressure value is corrected, the recovered carbon black actually performs better than the normal carbon black. So I hope that we can repeat that test and do the full processing of, I think, 200 grams master batch again with those two carbon blacks, because I think actually that alpha carbon recovered carbon black has pretty good dispersibility. Now, the application of films is very interesting for black master batch. And here the haze or the opacity is very important. This can be measured by the ASTM method D1003. And we measure the haze and the luminous transmittance of extruded LDPE cast film. At 1% pigment addition and 50 microns film thickness, this has to be standardized so that we can compare different films. Also here we can see on the left hand side, we can see the film with the recovered carbon black and the film with the Huff carbon black, medium color carbon black. And the recovered carbon black is pretty good. It's even slightly better than the medium color carbon black. And the last is the color measurement. For the color measurement, we injection mold plates, and they have about a 4 millimeter thickness. So we don't have any transmittance of the color. We don't go through this plate. And we measure the L star, A star, and the B star with a standardized D65 light source. And we see that actually between the recovered carbon black and the virgin carbon black, there's virtually no difference in the L. Also, the delta E just for A and B is very small, 0.2. It is barely visible. This is pretty good result in extrusion dispersion, in opacity for the film, and also in the color. Now let's put that again into the slide we had seen early on, and let's compare how black this recovered black master batch really is. And we can see it's not quite black because it is a gray pigment rather than a black pigment. The ash content, we could consider the ash as a white pigment. So it's a mixture of a black pigment and a white pigment. And this is because this particular recovered carbon black was made from European tire feedstock. Furthermore, European car tire, PCR, passenger car radial tire feedstock, which has a high ash content because it has a high silica filler content in the tread. The RCB has only 80% carbon black. Also, I don't think it was milled very, very finely. I think there's some improvements possible, both on the feedstocks, on the carbon black content, but also on the milling. We're going to see that in a moment. What kind of improvements can we do? So we talked mainly about increasing the carbon content, and there's 3 levels of feedstock control. So on the first and most simple level, we can control what type of tires goes into the pyrolysis. And we said that the passenger car tires have the silica content, truck tires have less silica content. So we could do actually a recovered carbon black for coloring, which is based on truck tires. At this point, whole truck tires. In the second level of precision, we can analyze the tires with a thermogravimetrical analysis, and we can determine what is the carbon content we get, what is the ash content we get for the resulting recovered carbon black. And the best and most, the deepest control is with XRF analysis, when we actually measure, and we can do that online. We measure online each tire how much silica content and other inorganic content it has. There's one recovered carbon black company, Black Bear Carbon, who has a patent for that. And they analyze the tires as they go on the conveyor to sorting. And you might know they have two ranges. One range with normal silica content and one range with low silica content, which of course will be better performing in coloring applications. Now, Black Bear Carbon are specializing on paint applications, but this kind of low silica RCB would be nice for plastic applications as well. Of course, we can correct the ash content after the pyrolysis, but as a chemical engineer and process engineer, my experience is the earlier you correct for any kind of problems, the cheaper it is and the most efficient the method is. So there's an acid-based method for ash leaching, and depending on how much carbon content you're happy with, if you want to have 98% carbon, you might add some 400 euros a variable OPEX cost to the process. If you want to be 99.5 and higher, you're certainly adding 2,000 euros per ton of the recovered carbon black. And also, if you think about the large volumes of recovered carbon black in a typical plant, thousands of tons, if you have to run all these through an acid and a caustic, this is perhaps has also some safety issues. There's a new method, hydrothermal ash leaching. Hydrothermal meaning just with water and temperature. It promises to be cheaper, about 200 euros per ton, but that particular company is only a lab scale, and I find they first have to prove the commercial viability for thousands of ton per year plant. The second stage of improvements for the recovered carbon black master batch is increasing the amount of the high color carbon blacks. So we need to see, this is about the particle size and the microparticle size. Where are high color carbon blacks? And these are predominantly in the truck tire tread. So this is just the tread which has ASTM N100 or N200 range of carbon blacks. And they typically have a microparticle size between 20 and 30 nanometers. The smallest the furnace process can produce is 20 nanometers. Now let's move to the right-hand side where I show the jetness, which is called MY. And the jetness in function of the microparticle size of the carbon black. And the jetness is a measure for the jet aspect. There's a blackness as well. I won't go deep into the difference between the blackness and the jetness. This is taken from a very nice article written by the carbon black maker Orion Engineered Carbons, Black the Fine Details, in the European Coatings Journal in May 2019, so quite recent. This is for a coatings application, although you could argue it's a plastics application as well. It's a polyurethane coating. Now, I calculated, based on the equations in that article, I calculated the L star value so that we can relate, because we looked at L star and we said everything under 5 is black, everything under 1 is deep black, and 0, which will never be accomplished, but 0L would be the super deep black. And here we can see the different particle sizes, 51 nanometers, that could still be a furnace black, 25 nanometers as well, 20 nanometers. So 20 nanometers gets us to L star of 0.16 in the polyurethane coating. Let's keep that in mind. But everything lower than that, the 70 nanometers, 30 nanometers, and the 11 nanometers, these are from a different process. And the process is gas blacks. The gas blacks can produce much smaller particles, and we can get lower than L.15. And these are the really super deep black carbon black pigments. Of course, this is on the complete other side of the spectrum than we have with recovered carbon black. But keep in mind, the possibility of having truck tread and making recovered carbon black just from truck tread will get us into a particle size, microparticle size of around 20 to 30 nanometers, which is good for the color and for the jetness. And then, of course, we have to mill. We have to mill very finely. Now, milling is not really going on the blackness. This is really the micro particle size, but the milling is more the recovered carbon black aggregate size. But the aggregate size also plays on how we can disperse and how we can distribute the recovered carbon black in the master batch and in the final application. Here, I would recommend a milling below 10 microns. Let's look at the optimized recovered carbon black master batch. So we said feedstock is pure truck tread. So we get an RCB with about 94% carbon black, which is very high. There's only 6% ash content or whatever, 5% ash content and maybe 1% moisture. This is milled to clearly below 10 micron. And what it results into, we have 44% less reflectance. Keep in mind, black is about absorbing the color and white or gray is about reflecting the color so that we can see it. And you can see already it is much darker. However, if we compare it on the left-hand side to the jet black, we can see that still it is gray. It is a dark gray, but it is gray rather than black. But you can see also there's a net improvement over the standard high silica passenger car tire recovered carbon black. So I think this is a very nice result. I think this can be further tweaked, but just to show you a nice improvement. The last slide of my presentation is about regulatory aspects. And the biggest or the most important is the food contact, because many of their plastics applications are in food contact or skin contact of any sort. And there's different regulations in Europe and the US. And there's a traffic light. You can see the EU food contact is possible. There is recovered carbon black manufacturers that actually give an opinion about the food contact and give green light. The specification is in this slide. So the toluene extract needs to be smaller than 0.1%. The cyclohexane extinction at 386 nanometers needs to be below 0.02 for the 1 centimeter cell or below 0.1 for the 5 centimeter cell. Benzoapirin, the most nasty compound of the polycyclic aromatic hydrocarbons, needs to be below 0.25 ppm, milligram per kilograms ppm, or 250 parts per billion. We might have microparticles between 10 and 300 nanometers, aggregates between 100 and 1,200 nanometers, which is 1.2 micron, and agglomerates bigger than 300 nanometers. And some recovered carbon blacks would certainly fit that scheme. And we have a limitation to the addition. We can have maximum 2.5% weight of the carbon black in the final item. So this is green light, thumbs up. In America, the regulation is much more stringent, and the FTA food contact is not yet possible. In my opinion, I haven't seen any recovered carbon black player that is fulfilling the very strict requirements of FTA food contact. The total pH content needs to be below 0.5 ppm. I think the best I've seen is 1 ppm. The benzoapirin content needs to be lower than 5 parts per billion. This is super, super low and very, very difficult to achieve. Again, we have a limitation for the maximum carbon black or recovered carbon black content in the final item. The third regulatory aspect is very often master batches require a declaration, or the packaging customers of the master batch require a declaration that the master batch is heavy metal free. And this is the European Directive 94/62 CE, Article 11, Paragraph 1, and the relevant Annex 2. And this is about the absence of chromium-6, lead, cadmium, and mercury. So thumbs up. You might have worried that in recovered carbon black, we have zinc, which is a heavy metal. This is not considered in this directive, so thumbs up. However, zinc is subject to restrictions also to the under this legislation. And the zinc sulfide, we need to make sure that the specific migration limit, SML, is lower than 5 milligram per kilogram, so 5 ppm expressed as zinc. So the zinc sulfide should not migrate out of our master batch or out of our plastic film or plastic product. Thank you very much. I will now go to the question and answer session. So you have communicated a number of questions in the comments, and I will read them and answer one question after the other. Kane is asking, with RCB, does anyone notice having to change screen packs more often? I would say that the problem is that not every RCB is created similar. It depends on the feedstock, it depends on the milling, it depends on the refining. So if we don't mill to underneath 10 microns, surely, and we screen with a screen over the milling size, we will have a pressure buildup, and then we have to change the screens more often. So fine milling is important. Annie from Graviki is asking, what are some good RCB making companies in India? I think in the audience there are some good RCB making companies. Look at that slide and look up and contact those people in India. There is good RCB makers in India. Again, Annie, does Cabot make recovered carbon black? No, Cabot is an integrated carbon black maker. They have a plastics unit called Cabot Plastics that is doing plastic master batches. Until last year, they were only allowed to use Cabot carbon blacks. Now, with the recovered carbon black master batch, that's the first time they allow non-Cabot carbon blacks to end up in the master batch. But no, they haven't integrated in recovered carbon black. I think also they are the least likely to integrate into recovered carbon black. I see Billa and Orion more likely to make that step. But ultimately, it will come. It's a question of scale, and it's a question of recovered carbon black quality and quality consistency. Then again, Kane from Orion Engineered Carbons. Any chance you know the MY value of these blacks? Yes, remember that slide and from the Orion Engineered Carbons article. I don't have MY values for recovered carbon blacks, so that would be the next step, going one level deeper than this webinar, and spending some money with recovered carbon black producers to do a really good color analysis, maybe a design of experiment, how we can improve the color if we turn certain knobs on feedstock control, process control, and refining. I would love to do that. Annie, also, is recovered carbon black such a great opportunity? Why Cabot Billa don't do this business? Just curious. I replied it already. It's a question of scale. It's a question of quality, consistency, and of course reliability and the trust those companies have in recovered carbon black. Keep in mind, most of the recovered carbon black makers are small startups, and they have only one site. And for big companies like Cabot or any big customer like a tire company, business continuity is very important. And a supplier that is single sourcing from one side is always a little bit of a risk. I think it will come. I think tire makers will jump on recovered carbon black more and more. And there will be more available volume as well in the next couple of years as we see recovered carbon black maker finishing their plant builds and going to market. I'm working with quite a few clients on exactly that topic. Ani, again, from Graviki, what do you think about advanced applications such as graphene and carbon nanotubes? Now, I personally haven't seen these kind of applications. I've seen a collaboration for activated carbon, but not graphene and carbon nanotubes. I think that would be the next step, maybe interesting application. I think we'll have a question about conductive recovered carbon black as well. This is connected because graphenes and carbon nanotubes certainly are used for increasing conductivity in polymer matrices. Then Annie, again, thanks for all these questions. Can recovered carbon black be also used to make laser toners? Honestly, I don't know. I looked at recycling laser toner cartridges and the content of laser toner cartridges, because they're never empty. When the laser printer says they're empty, there's still some material in there. I think this is a super niche. I think these are super small particles. I think they're way smaller than anybody is milling, but I would have to dig into that. Also, these particles are surface treated. It's not just carbon black. This is also other other black pigments, not only carbon black, and they certainly are surface treated for the high performance. Then Bob from Rotorwave Scotland. Martin, if passenger car tires are high in silica and truck tires are lower, does it make more sense to process them separately? Yes, absolutely. As I mentioned, that is the first stage of controlling the feedstock, and the second stage is actual TGA measurements or even XRF measurements. With X-ray fluorescence to determine the silica content. But it would be a very good first step, because you don't even need equipment to tell a truck tire from a passenger car tire. Then Alpha Carbon is asking, thank you, Martin. Lowering the RCB particle size may increase the melt index. What is a good compromise to efficiently process it? I think ultimately the processing conditions have to be adapted. But what I see, I wouldn't see a strict correlation between the RCB particle size and the melt index. I would see a correlation between the carbon black structure and the melt index. So I think this has to be tested again, maybe with a design of experiment, several tests, and then do a multi-regression on it to see what is the biggest effect on the melt flow index. Then Peng from Farrell, can RCB be used for conductive applications? That's a very nice question. I have, in my web shop, I have a report on conductive recovered carbon blacks. I can tell you the market is very small. It's about 1% of the total market for carbon blacks. And so for recovered carbon black is super small. And of course, we need to do very specific things. And the milling alone and the pelletizing is not sufficient. So we need to start with the feedstock control, the process control, and then milling. But we also need to take out all the ash. We need to spend those 2,000 euros per ton of recovered carbon black to get to 99.5+% of carbon. And then we need to activate. We need to go in with steam or carbon dioxide at high temperature and high pressure and crack open all the pores in order to increase the surface. So that we get into the performance of conductive carbon blacks. So yes, it can be used, but it's a big circus to achieve that. I only know one company that is doing that, and that is Caltire in Canada, who is building a site in Chile. Their feedstock is mining tires, so it's a good starting point. But again, they need to do a really, really big process in order to get the recovered carbon black to be conductive. Conductive applications, I mean, there's on the simple level and relevant to this webinar on plastic applications, the simplest level of conductivity might be anti-static masterbatch, which is discharging the static, typically built up by loading up any polymer films. You might have seen films clinging together that might be static electricity. But on the more exciting applications, these are battery applications for example, lithium-ion batteries. We all depend with a mobile phone or the electric cars. We depend on the batteries and on the power, and also the range of the batteries are limiting the range of the utilization of the electric vehicles. So this is very, very exciting application, and maybe Tesla could use RCB sometime in future. Now, Ravi from Capital Carbon India is asking, do masterbatch industry accept material in powder form or in pelletized form? I would say pellets are much easier to handle, certainly lower dust. If you would discharge a big bag of powder recovered carbon black, you have a big cloud of carbon black. It's about the safety and also environmental aspects. So pellets are clearly preferred. However, they shouldn't be too hard. So if you do the dry pellets, which is a bit more like a tablet pressing, this might be too hard to be dispersed with the dispersive elements of a twin screw extruder. Francois from Clean Carbon Conversion, based on the current market size in the order of 5 to 20 kiloton a year, what do you think is the market cap or potential demand for RCB in plastics? Now, I haven't actually filtered down to RCB in plastics. I could, because I have the customer list for Europe and North America. I just have the total figures, and I told you European potential demand is 180,000 tons. Now, admittedly, most of this is tire, and number two is rubber, and only then comes the masterbatch industry. But there is thousands of tons potential even in the plastics industry. Also knowing that the supply is much less than the demand. Kinan from Turkey, EcoSafe in Turkey. Can we produce water-based carbon black from pyrolytic carbon black? Now, probably you mean carbon black that can be used in water-based paints or water dispersions. These typically on the normal carbon black side, as well as the recovered carbon black side, would require post-treatment. And a normal carbon black is oxidized. And the recovered carbon black, we could do a gas treatment with ozone, which brings on oxygen at the surface, which probably was detached in the pyrolysis process, because the carbon blacks after the pyrolysis process, some of the surface groups, they just burnt off under the conditions of the pyrolysis process. So we bring back the oxygen, we bring back the oxygen-hydrogen surface groups, which are helping us to get the surface hydrophilic, so dispersible in water. Ravi from Capital Carbon, is there any difference in tin factor and powder and pellets of RCB? No, they shouldn't, provided that you can disperse the pellets as good as you can disperse the powder. So there shouldn't really be a difference. If you have pellets too hard and you don't disperse, you will certainly see the lower tin factor. That's for sure. Kane from Orion Engineered Carbons, tin factor with powder and bead depends on the ability to disperse properly. That's just what I said. Martin discusses the powder being needed for milling equipment that has less energy. The milling plays a role, and the pelletizing, of course. In the end, in the end application, you need to disperse both carbon black and recovered carbon black appropriately so that you can have the color performance. Annie saying, we're trying that market. I think you mean the conductive or the water-based coatings market, and would love a webinar on that. Yeah, maybe one of my next webinars, Watch the Space, could be about inks, water-based inks and water-based coatings. It's a very tiny market though, so maybe there's not a lot of people who want to know that apart from you, Annie, and some paint makers. Ravi from Capital Carbon, Martin, for pelletization, what is the best binder for plastic uses? So the binders used in carbon black tend to be molasses, so sugars, waste from the sugar industry, or lignosulfonates, added at a faint concentration, I think below 1%. I don't remember the exact percentage. I have heard of recovered carbon blacks that didn't need any binder for making pellets, that have really nice pellet and also the pellet hardness without any binder. So I would say it depends, but starting point would be molasses and lignosulfonates. Bob from Rotawave, what do master batches think of recovered carbon black versus virgin carbon black? I think with that webinar, I could show you there's at least 5 of them that already have recovered carbon black master batches. They see it as an eco product, and we all know, we consumers, it's more important, more and more important for us to have sustainable materials. We also know that there's a lot of plastics bashing going on, where plastics in many cases are the most environmentally sustainable solution. The problem is the behavior of the consumer, what they do after the end of life of the plastics product. Does it go into recycling or doesn't it go? So I think master batches see the opportunity, and I've been told by some of the master batches who don't have a recovered carbon black master batch that they surely want to make such a product. So I think all doors open to that product. However, the product needs to perform. That is clear. It needs to provide color. It needs to be dispersible. It shouldn't contain any nasty stuff like PAH or crystalline silica. So we have to engineer a good product for those coloring applications and the master batch companies. François again from Clean Carbon Conversion. Do you have any data regarding the ash composition affecting the performance of the recovered carbon black? Are there specific chemicals, ashes, metal salts, which affect the performance severely? Now, bear in mind that in plastics and in master batch, our primary goal is coloring and tinting. And the ash, as I said, is more of a white pigment than the black pigment. We have already mentioned we want as little ash as possible. But within the total ash component, I would say the components that have less white aspects, less refractive index, they are better. So the less refractive index the ash composition has, the better. But actually, I don't have data, so this is an estimate from my side. Giovanni Michetti from Boulder and Kylos Master Batch. Does recovered carbon black have some UV protection as virgin carbon? Yes, it does. And I've seen some mentioning in the applications for recovered carbon black master batches in pipe. Some pipe applications, the pipes are extruded and then they're just put outside and they're exposed to sunlight. And it can be weeks before they're being put underground. And in that case, they need UV protection. I think there's also specific standards by pipe manufacturing associations. But basically, UV protection is the same as black color, because what we want is the carbon black and the recovered carbon black to absorb UV radiation. So the higher the carbon content is and the smaller the particle is, the better is the UV protection. Also, again, same as for the color, the dispersion and the particle size, which allows us to have a better dispersion and better distribution throughout the plastic part, that can help. Ravi from Capital Carbon, does sulfur present in recovered carbon black affect in any way the plastic master batch performance? I have not heard. As long as it is non-leachable and stays within the plastic matrix, I think it is not a big problem. But I would put that question to the master batch companies and make sure that they don't have any problem with the sulfur content. Vishesh from Finster Carbon, is there any proven technology supplier for acid-base leaching or hydrothermal ash leaching? I don't think this has gotten out of the academic laboratory area yet. There's a number of academic articles on acid-base leaching. I think Caltire have developed that for the conductive recovered carbon black. I haven't seen the build of Caltire in Chile, and of course they're slowed down because Chile is not only in the COVID-19 crisis, but they're also close to a civil war because of the social differences in the Chilean population. So they're slowed down in their build. The hydrothermal ash leaching is really only at kilogram stage at the moment. It's quite promising. I like to see it. But they need to prove the commercial viability for 1,000 tons or 10,000 tons. Vishesh again, does air gravity separation cyclone work to reduce grit level? Now, this would be an interesting thing if you mill fine enough, whether you could separate actually grit and ash and separate those from the recovered carbon black. That would be a very nice research project. Peng, I think I had that question already. Can RCB be used for conductive application? Yes, exciting application, but the market is very small, as we said. Derek from Colloids, do you have any data on functional groups on the carbon black surface and how this compares with standard furnace carbon black? I don't. My information is, I personally don't, but my information is that many of the surface groups are actually being burnt off under the pyrolysis conditions. However, I would recommend reading an academic article by Christian Roy, which is something like energy science of carbon blacks and recovered carbon blacks, and measuring the specific surface energy, not the surface groups, but the surface energy of the different types of carbon, which are both on the recovered carbon black and the normal carbon black. And he might have something on the functional groups as well. Derek, again, can you circulate all heavy metals? You mentioned 2011, but not the norm EN 713 regarding barium, chromium-3, lead, and organotins. No, I haven't mentioned that because I see a lot the heavy metal being specified in master batches, and the norm I quoted. This other norm I personally don't know. But starting from the composition of rubber compounds in the tire, you have very little barium, chromium-3, lead, and organotins, and this is what we recover. So personally, I wouldn't see a problem for fulfilling that norm as well. Of course, that has to be tested, that has to be analyzed. And the last question, also from Derek, do you have data that you can share about the carbon dioxide savings from using RCB? Now, I quoted the master batch companies and the carbon dioxide saving they advertise. You might understand that the carbon dioxide burden of the recovered carbon black also depends on the thermal efficiency of the process. So what I see, if you have a batch discontinuous process, I see values of 0.4 tons carbon per ton of recovered carbon black, which is already 2 tons less than the virgin carbon black. And I see 0.2 tons of carbon dioxide burden in the case of continuous processes. And I have a third figure, which is, I think, 1.2 tons carbon per ton of recovered carbon black for a double pyrolysis. This is when you have 2 kilns one after the other, in order to get a really, really dry recovered carbon black with a very, very low pH content. And of course, if you have 2 times the pyrolysis, you need to heat up 2 times and you're creating a little bit more carbon dioxide. Still half of the carbon burden of virgin carbon black. So I'm wrapping up the question and answer session. Thank you very much, everybody, for attending, and I hope you join me on my next webinars.